Okay, good morning everyone, and I welcome you all in this class of condensed matter physics course. And today our topic is Fermi surface and Brillouin zones. So in couple of slides, I will summarize the previous class so that will form a basis of the today's lecture. So and you will recall what we discussed in the previous class. So in the previous class, we discussed about the motion of electrons in a periodic potential. The periodic potential is created by the ions or atoms which possesses the translational symmetry, means that ions or atoms are located at a fixed distance with respect to each other. So we saw the shape of the periodic potential, and then we discussed one of the very famous model named as Kronig-Penney model, in which the whatever is the shape of the periodic potential, and it was considered to be a square well potential kind of form, in which, as you can see from the figure, there are square wells which are separated. The two neighboring square wells are separated from each other by a potential barrier. So this means that at the ionic site, or at the atomic site, the potential goes to infinity, goes to negative direction, and in between the ions, the potential or potential energy is equal to zero. So this was what Kronig and Penny considered to explain the behavior of electrons in a periodic potential. So, and we have seen that when we consider this Kronig-Penny model, then we saw that there are certain allowed ranges of energy with respect to the wave vector, and there are certain forbidden energy ranges in which the solutions of the Schrodinger equation do not exist. So if we plot that in terms of the extended zone scheme, where only one part from each zone is taken, so we can see that at the zone boundary there are gaps. There are gaps in the EK diagram. On the y-axis represents the energy, whereas the x-axis represents the reciprocal lattice, the wave vector or the momentum vector, momentum space. So this is the extended zone scheme, in which we can see at the integral multiple of pi over a. We see there is a discontinuity in the EK diagram. Had it been for the free electrons, then uh, we should have observed a parabola which is shown here. So this parabola is a continuous parabola for free electrons. So, and in the previous class, we also discussed about different zone schemes, namely the extended zone scheme that is shown here. And we also discussed the periodic zone scheme, in which this graph is going like this, like this. It is a wave kind of thing, and it goes from minus infinity to plus infinity in all the directions. Similarly for this, that is the repeated zone scheme or the periodic zone scheme. Now, we due to the translational symmetry possessed by the underlying lattice, we can see the EK diagram will also possess the translational symmetry. This means that we need not worry about higher zones, and we can transfer the higher zones into the first Brillouin zone with the help of suitable reciprocal lattice vectors. So this picture shows the zone scheme in the that is known as the reduced zone scheme. So what is done is, here this portion has been translated to the first Brillouin zone by a suitable vector that is 2 pi over g. So for example, you consider this point. If I translate it by minus g, that and g is equal to 2 pi over a, or integral of 2 pi over a. So this point will come here as is seen, and this point will come here. So this part represents this portion, and this portion is represented by this part. Similarly, the higher zone higher zone parts in the extended zone scheme can be translated to the first Brillouin zone like this. So this is whenever everything is contained in the first Brillouin zone, that scheme is known as the reduced zone scheme. So this is the first band or first range of allowed energy. Allowed energy, it is from 0 to up to this value. Then we see there is a gap. There is a gap. So this means that it is the forbidden region where the solution of Schrodinger equation does not exist. Then we have the second band and the gap, and the third band. We can see that the width increases as we go to the higher band, and the gap, the forbidden gap value also increases. So we also discussed the empty lattice model. By empty lattice model, we mean that there is no underlying lattice. It is only the free electrons. So that's why the name empty lattice model. There is no lattice, or the electron is moving freely. So when it is moving freely, so it will have a continuous parabola shape of the EK diagram, that is also known as the dispersion relation or dispersion curve. And in the empty lattice model, what is considered is that the periodic crystal potential is vanishingly small, or we can say it is equivalent to zero. There is no periodic potential created by the underlying lattice. Then we will get the shape of the curve that would be in the shape of a parabola. So what we can do is that uh, uh, if we consider any energy point at a particular wave vector k, that can be translated to the first Brillouin zone with the help of the reciprocal lattice vector g, where g is integral multiple of 2 pi over a. So you can see that in the empty lattice model, the portions, the different portions or the various portions of different Brillouin zone can be translated to the first Brillouin zone. And you see, because it is the dispersion relation in the absence of periodic potential, so there is no gap. There is no gap that exists at the first Brillouin zone boundary. So the gap at the zone boundary will exist only when we have the periodic potential. So in the previous case, we considered the periodic potential. That's why there was gap at the zone boundary. But if we consider the empty lattice model, then there would not be any gap. So this is the EK diagram of a free electron uh, in uh, in the extended zone scheme and in the reduced zone scheme. Then we considered the nearly free electron model, and in which we considered that the kinetic energy kinetic energy of the moving electron is greater than its potential energy, and this potential energy arises due to the interaction of electron with the positive ion core. So that is the model of nearly free electron model, in which a weak periodic potential is considered. And when we describe the nearly free electron model, that also showed that the gaps exist at the zone boundary, that is at the integral multiple of pi over a. And we can see the two things have been plotted simultaneously. That is, this blue line represents the free electron behavior. It is shown by a parabola, and then superimposed over it is the EK diagram when we consider the weak potential or the nearly free electron model. So we can see that whenever we are deep inside the Brillouin zone, the two curves are matching with each other. So you can see the free electron model or the empty lattice model and the nearly free electron model. They match with each other deep inside the Brillouin zone. But when we approach the zone boundary, you see there is a significant deviation. There is a significant deviation. And in the previous class, we proved that whenever K is inside the first Brillouin zone, so all the energy levels, so the energy would go down, and if uh, we are in the second Brillouin zone, but close to the boundary of first Brillouin zone, then the energy would go up. The energy would go up, and similarly, you can see here whenever we are at the other side of the whenever we are at the second Brillouin zone boundary, so energy would go down, and in the start in the on the other side of the second Brillouin zone, that is in the third Brillouin zone, energy would go up. So still it can be transferred because it is in the extended zone scheme, and the same can be transferred to the first Brillouin zone, and whatever we get, this is known as the reduced zone scheme. So higher bands can be transferred to the first Brillouin zone, and we can construct the reduced zone scheme for nearly free electron model as well. So depending upon what is the shape we are getting from the considering these models like chronic penny model or the nearly free electron model or the tight binding model, that is the sixth assignment for you. So we can uh, tell or we can describe whether a solid should be an insulator, semiconductor, or a metal or a semi-metal. So, for example, this is the EK diagram. This is the EK diagram in the reduced zone scheme for a particular type of solid, and you can see that this sky blue region, it tells us that the first band is completely filled. The first band is completely filled, and the second band is separated from the first band by a forbidden energy gap. So if this band is, we are considering the situation at T is equal to 0 Kelvin. If the value of this forbidden gap is very large, so the electron cannot go from this state to this state when the temperature is increased, because the band gap is very higher. So that's why the material will remain insulator, because this band is completely filled. So if we apply electric field or if we heat the solid, then these electrons do not find empty states where they can move. But if the gap is smaller, so thermal energy would be sufficient to cause some of the electrons to go from uh, this band to this band. So then we will have finite number of electrons in this band. This is known as the conduction band, and this is known as the valence band. So such type of materials in which the band gap is smaller than a particular value, generally for semiconductors, the band gap is uh, equal to or lower than 3 electron volt. So if such is the situation, then that material would be called as semiconductor, otherwise it would be an insulator. In case of metals, we can have different type of scenarios where the, for example, one band is completely filled and the other empty band, they can overlap. So you can see in this middle diagram that the upper band is overlapping with the lower band. So this means that we have some empty states just in front of the filled states. Therefore, electrons can transfer from these states to the empty states. So such type of EK diagram belongs to what we call as semi-metals. So for semi-metals, please understand the difference between semi-metal and semiconductor. It is a very good question you may be asked somewhere. In a semiconductor, there is a band gap between the conduction band and with the valence band. However, in case of a semi-metal, the conduction band and the valence band, they overlap. That's why some of the electrons of the valence band can be transferred to this conduction band, and otherwise it should have been insulator if there is no existence of energy gap. So it is called semi-metal. So for example, bismuth is the example of a semi-metal. There are other semi-metals also, beryllium also example of semi-metals. Or we may have band situation like this in which the lower band is completely filled and we have already many electrons in the conduction band, and if we raise the temperature or we connect our solid with the external battery, so these electrons find empty states and they can move easily to the empty states. That's why the conduction is really possible. It is easily possible, and it is again another example of a metal. So if we plot the contours of free electron energy, we know that E is equal to h cross square k square by 2m. So if we plot it in 3 dimension, it would be a sphere, as we have already seen from the discussion of Sommerfeld quantum free electron theory, that the electrons remain inside a Fermi sphere that has the shape of a sphere, but in reality, it is not so. It is not so. There are many metals except the alkali metals where this shape is not spherical, but rather it is distorted shape. And today, this we are going to see uh, how different shapes the different metals can have. So if we have the free electron model in case of 3 dimension, it would be a sphere, and in 2 dimension it would be represented by a circle, and this square shows the first Brillouin zone boundary. So depending upon the concentration of electrons, we may have the electrons filled up to the periphery of this circle, or up to this circle, or up to this circle, or like this. And depending upon how far this Fermi surface is, depending upon how far this surface is from the Brillouin zone boundary, we will see that the interaction of this Fermi surface with the Brillouin zone boundary will affect the shape. So this shape will be distorted. So for example, if we consider the monovalent atoms or the alkali metals like sodium, like potassium, then because in these type of metals, each atom contributes one electron, and their Fermi surface is completely circular or completely sphere, and it lies deep in the Brillouin zone. There is no interaction of the Fermi surface with the Brillouin zone boundary. But if we have another type of metals in which the electron concentration is more, so the area of the Fermi sphere would be large. That depends solely on the number of electrons, and when it is closer to the zone boundary, then it will interact with the zone boundary. The Fermi surface will interact with the zone boundary, and the shape of the, as you can see in the third diagram, that the shape of the Fermi surface will get distorted. Deep inside the Brillouin zone, it is circular in shape, but as we increase the concentration of electrons, the Fermi surface starts interacting with the Brillouin zone boundary and it's get distorted. So most of the real metals do not have spherical shape of the Fermi surface as predicted by the Sommerfeld quantum free electron theory. So that is again a shortcoming of the Sommerfeld quantum free electron theory. So depending on the direction of the direction in the Brillouin zone, we may go to a larger K before the states are perturbed. So this means, for example, if we are moving along this direction, so this is 100 direction, and we are having a value of K where we will encounter the Brillouin zone boundary and the gap would exist. But if we are going along the 110 direction, so this blue line represents the 110 direction. If we are going along the diagonal of this square lattice, then we will see that we can go a larger value of k, we can go a larger value of k before the gap exists. So here you see the k value is smaller when the gap exists, but along the diagonal we need to move a larger value of k, and then we will encounter the Brillouin zone boundary where the gap will exist. So we need to define what do we mean by Fermi surface. So a Fermi surface is a surface of constant energy in k space, and Fermi surface is denoted by a wave vector that is kf. So kf represents the radius of the Fermi sphere or radius of the circle in 2 dimensions. So Fermi space is the surface of constant energy in k space, and as we have learned that if our metal is at T is equal to 0 Kelvin, then Fermi surface separates the unfilled states from the filled states. If you recall, when we plotted the probability of finding the electron at energy level E, that was given by Fermi-Dirac statistics, and it was a rectangular shape at T is equal to 0 Kelvin. This means that all states up to Fermi energy were filled, and states above E is equal to EF were empty. So Fermi surface separates the unfilled states from the filled states at absolute zero. The electrical properties of metals are determined by the shape of the Fermi surface because the current is due to the changes in the occupancy of states near the Fermi surface. If you recall, when we discussed the Sommerfeld quantum free electron theory, we proved that not all the electrons, but the electrons lying in the kBt upon EF region of the Fermi surface, they participate. Only these fraction of the total number of electrons participate in the conduction. And they determine the how the conduction will take place in the metals. The free electron Fermi surfaces are developed from spheres of radius kf and determined by the valence electron concentration. So kf is proportional to the, if you recall, it was proportional to the n to the power 1 by 3, where n is the electron concentration, number of electrons per unit volume. All right, so now we are going to see first, though we already have understood how we construct the Brillouin zone, and then on the Brillouin zone, we will superimpose the Fermi surface, and we will see what are the consequences when we superimpose the Fermi surface over the Brillouin zone. So we consider this square lattice in which these open circle represents the reciprocal lattice points, and the Bragg reflection condition in the reciprocal lattice is 2 k dot g plus g square is equal to 0, and if you recall, this condition is satisfied if any wave vector uh, any wave whose wave vector starting from the origin terminates at the zone boundary, or in other words, if k terminates on the plane normal to g at the midpoint of k. So for example, if we are considering this point as origin, and we connect all the neighboring points, So this is the nearest neighbor, this is the nearest neighbor. Then we draw the perpendicular bisector along this direction, along along this direction, and along this direction. So we will form a Wigner-Sitzer for a square lattice. That is the first Brillouin zone. That is the first Brillouin zone. Then if we connect the second nearest neighbor points, then the perpendicular bisectors of these vectors will form the second Brillouin zone. And similarly, if we connect the third nearest neighbors and we draw the perpendicular bisectors, then we can form the third Brillouin zone, and so on and so forth. Higher Brillouin zone can be constructed in this way. So the first Brillouin zone of the square lattice is the area enclosed by perpendicular bisectors of this reciprocal lattice vectors G1. And so G1 is in this direction. By symmetry, it is in this direction. By symmetry, it is in the y direction and in the minus y direction. So these four reciprocal lattice vectors are represented by plus minus 2 pi over a kx and plus minus 2 pi over a ky. The second Brillouin zone is constructed from the vectors k2 when we connect the origin to the next nearest neighbors, and their perpendicular bisectors will form the second Brillouin zone. And the three equivalent three vectors equivalent to it by symmetry. And similarly for the third Brillouin zone, so the pieces of the second and third Brillouin zone are drawn in this figure. So you can see the white square that represents the first Brillouin zone, and these are the pieces of second Brillouin zone. These are the pieces of second Brillouin zone. So these are the isosceles triangles. These are the 1, 2, 3, 4. 2, 2, where 2 is written. They represent the pieces of second Brillouin zone. Similarly, we will have the pieces of third Brillouin zone, all represented by 3. So wherever you find 3 is written, that represents the portion of third Brillouin zone, and it is in the extended zone scheme. So you can see, except the first Brillouin zone, we have the second Brillouin zone in the pieces. One piece is lying here, the other piece is lying here, the third piece is lying here, the fourth piece is lying here. Similarly, for the higher zones, the pieces are lying at different locations. And so, for example, if we want to determine the boundaries of some higher zones, then we need to consider set of several non-equivalent reciprocal lattice vectors. So, for example, if we consider this piece of third Brillouin zone, then this is one of the boundaries of third Brillouin zone. This is this is the second boundary, and this is the third boundary. So these form the complete boundary of this portion of third Brillouin zone, and the corresponding vectors for these are 2 pi over k. So for example, this boundary is the half of G1. So this is represented by 2 pi over a kx. And then this, if I draw a vector from here to here and I perpendicularly bisect it, so it will be 4 pi over a ky. And this part will be formed when I connect this point to this point and perpendicularly bisect it. So I need to move along x direction, and I need to move along y direction. So its coordinates would be 2 pi over a kx plus ky. And because these are non-equivalent, you can see these vectors, their magnitudes are not equal. That's why they are non-equivalent reciprocal lattice vectors. Now we have understood how we form the Brillouin zone, different Brillouin zones, and now we need to superimpose over it the Fermi surface. The free electron Fermi surface for any arbitrary electron concentration is shown in this diagram. The free electron Fermi surface means the electron is free, and for the time being we are assuming that there is no underlying periodic lattice potential, only the electrons are free. And when the electrons are free, their Fermi surface is represented by a sphere in three-dimensional case, or by a circle in two-dimensional. So this is the Fermi. This circle represents the Fermi. Not it will not be surface, rather it will be curve in two dimension. In three dimension, it would be surface. And depending upon the concentration of the electrons in the metal, the radius of the Fermi surface would be determined. So in this example, you can see that Fermi sphere extends up to third Brillouin zone. The Fermi circle, this circle extends up to the third Brillouin zone. Uh, the total area of the filled region by the Fermi surface in K space depends only on the concentration of electron, and it is independent of the interaction of electrons with the lattice. What I am saying is that the area of this circle is solely dependent upon the concentration of electrons. More is the concentration of electrons, the larger would be the area of this circle. The smaller is the concentration of electrons, the lesser would be the area of this Fermi sphere. It does not depend, the area does not depend upon the interaction of electrons with the underlying lattice, but its shape. Here it is circular, but as I told you, different metals would have different shapes. So the shape of the Fermi surface will depend on the interaction of electrons with the lattice. And as we would see, the shape will not be exact circle in actual lattice. So now, as we have seen that when we are considering this picture, we can see that if we consider the second Brillouin zone, then its different parts are lying at different locations. So it is not a convenient thing, rather it is inconvenient. It is inconvenient to have sections of the Fermi surface that belong to the same zone appear detached. You can see they are separated from each other. This section is separated from this is separated from this. They are lying as if there is no interaction between them, so it is inconvenient, and they are detached from one another. The detachment can be repaired by a transformation to the reduced zone scheme. The procedure is known as mapping the Fermi surface in the reduced zone scheme. We need not do anything for the first Brillouin zone at it is complete in itself. What we need to do is, now with the help of the suitable reciprocal lattice vector, we will translate these sections into the first Brillouin zone. And remember that I have told you that area enclosed by all the Brillouin zones in two-dimensional is equal, and in three dimension, the volume of all Brillouin zones is equal. So if we translate this portion with the help of a suitable translation vector, so this isosceles triangle would be shifted here. It would be shifted here. If we translate it, this portion would go here. If we translate it, it will come here. And if we translate it, it will come here. So all these four sections of the second Brillouin zone, they will completely occupy this first Brillouin zone, as the area of first Brillouin zone is equal to the second Brillouin zone. Similarly, if we translate the, the sections of third Brillouin zone, so this section would come here and this section would come here. Similarly, when we translate all the remaining sections, they would completely fill the area enclosed by the first Brillouin zone. So this is what has been shown here. So this is 2A section. This is 2A section that has been translated and it comes here. Similarly, other 2B, 2C and 2D. And you can see they enclose, they cover the complete area of first Brillouin zone. Similarly, when sections, different sections of the third Brillouin zone are translated to first Brillouin zone with the help of suitable reciprocal lattice vectors, they cover the complete area of first Brillouin zone. Now, this is what we have seen, that the sections, different sections of a particular Brillouin zone can be translated to the first Brillouin zone. Similarly, we would like to see that from the extended zone scheme, how the different portions of the Fermi surface which lie in different Brillouin zones, they can be translated in the first Brillouin zone. So you look at this picture. The first Brillouin zone is completely covered by this Fermi circle that is represented by this shaded region, shaded circle. So you can see this circle completely encloses the first Brillouin zone. So this is what is shown here. This is what is shown here. Now, if we translate the portion of Fermi circle that lie in the second Brillouin zone. So please see the movement of the cursor. This is the portion of Fermi circle that lies in the second Brillouin zone. Similarly, this is the portion of the Fermi circle that lies in the second Brillouin zone. So these portions, with the help of suitable reciprocal lattice vector, they can be transferred to the first Brillouin zone. So this is in the reduced zone scheme. Whenever this part has been transferred, and you see some empty region is present, remember, we are now translating the Fermi surface, not the Brillouin zone. So we can have the empty circle. And when we transfer the Brillouin zone, parts of the second Brillouin zone, it covered the complete area. But now we are translating the sections of the Fermi sphere. So we will have some empty region. The states, the shaded areas, these are the shaded area, gray in gray color, they represent the occupied electron states, and parts of the Fermi surface fall in the second, third, and fourth zone. The first zone is entirely occupied. The second zone, when translated to the first zone, you can see this area remains. So these represents the electron-like states represented by gray color, and the white region, it represents the hole-like states. And you see they have very sharp corners, and later we would notice that when we apply the periodic potential, then their corners will not be as sharp. They will form the rounded shape. This is the third portion. This is the portion of third Brillouin zone that has been translated to the first Brillouin zone. So the shaded region represents the third Brillouin zone, and we can see that after even transferring the third Brillouin zone to the first Brillouin zone, their sections are completely lying away from each other. They are detached from each other in the reduced zone scheme. But if we look this figure in the periodic zone scheme, then this figure would like something like this. This would form a lattice of rosettes. You see, it is kind of a rose. So this is the third Brillouin zone in the periodic zone scheme. It is in the periodic zone scheme, and we would see it how we can form it, how we can form a rose type of thing of third Brillouin zone in the periodic zone scheme. And that would be understood with the help of Harrison construction. Harrison construction. So one scheme we have seen, that is the mapping zone scheme, and the similar scheme is the Harrison construction. There is another way to represent the Fermi surface in the reduced and periodic zone scheme. Fermi surfaces for free electrons are constructed by procedure that is credited to Harrison. So this is the diagram of Harrison construction, and we will try to understand it, how we can form this. The reciprocal lattice points of a square lattice are determined. Now we are trying to explain the procedure for Harrison construction. So first we need to find all the reciprocal lattice points, and free electron sphere of radius appropriate to the electron concentration is drawn around each lattice point. So you can see that depending upon the concentration of electrons in the present in the solid, we draw the sphere or circle around each lattice point. So you can see that around each reciprocal lattice point a circle is drawn, and you can see that wherever these circles are cutting each other, what you form is the third Brillouin zone. This is the same thing. This is the same thing. Okay, so you can see that this is in the third Brillouin zone in the periodic zone scheme constructed with the help of Harrison constructor. Excuse me. Any point in the K space that lies within at least one sphere correspond to an occupied state in the first zone. Points within at least two spheres correspond to occupied states in the second zone, and similarly for points in the three or more spheres. So for example, you see these points in the white region, they are common to both this circle and this circle. That's why they will form the second Brillouin zone. They will form the second Brillouin zone. Similarly, what I am saying is that points which lie in the common area of three circles, they will represent the portion of third Brillouin zone, and like this. So for example, here you can see three circles are cutting. That's why these are the regions, these are the points of third Brillouin zone. So we try to understand it in more detail. We have found we have a square lattice in which we have noted down all the reciprocal lattice points. We take a reciprocal lattice point and we construct the first Brillouin zone, and we draw the Fermi circle around this lattice point. The radius of this circle depends upon the concentration of electrons present. So the black square is the first Brillouin zone, And the blue circle is the surface of constant energy for free electrons, and the shaded area represents occupied electron state. Let me tell you that still we are considering the free electron. That's why it is in the shape of a circle. When we consider the periodic potential, then it would be perturbed. It will not be in the form of a circle. So then we construct all the spheres around each lattice points, all the spheres around the lattice points, and the blue lines, you see, the blue lines are the Fermi surfaces for the free electrons on the second Brillouin zone, and the shaded area represents the occupied electron states. So we have seen such type of picture previously in the reduced zone scheme, and whenever we repeat it, we get it in the periodic zone scheme. So this is the same thing. This is in the reduced zone scheme, and the same thing has been shown here in the periodic zone scheme, and the periodic zone scheme has been made with the help of this Harrison construction. Similarly, for the third zone, we can construct the blue lines are the Fermi surfaces for free electrons that lie in the third Brillouin zone, and the shaded regions, they represent the occupied electron states. Then we can have the part of the fourth Brillouin zone in the periodic zone scheme. So again, the same thing that in the reduced zone scheme, it would be like something like this. So this is this represents capital represents the portion of the Fermi sphere lying in the second Brillouin zone, and small letters represents the portion of the Fermi circle lying in the third Brillouin zone. So they can be translated in the reduced zone scheme. So this portion A would come here, C would go here, B would come here, D would come here, and similarly the small letters. And this we have already seen how we can transfer the part of the Fermi circle or Fermi surface that lie in the second Brillouin zone, and they will form. So this blue line that will represent the boundary of the Fermi surface of the second Brillouin zone. Similarly, this will represent, this blue line here will represent the boundary of the Fermi surface in the third Brillouin zone, fourth Brillouin zone, like this. So this is all in the second Brillouin zone in the periodic scheme, third Brillouin zone in the periodic zone scheme, fourth Fermi surface in the periodic zone scheme. I told you that for a free electron model, these corners are very sharp. But when we consider the nearly free electron model, or when we consider a periodic potential, then their corners are not as sharp. They form whatever, they convert into a rounded shape. So here you see it is in the rounded shape. Here also the third zone is also in the rounded shape in the presence of a weak periodic potential. Also the second zone, the energy increases toward the interior of the figure. This arrow represents the increase in energy, whereas in the third Brillouin zone, the energy increases outward. A Fermi surface like that of a third zone, because the shaded region represents the all occupied states occupied by the electrons. So these are known as the electron-like states, whereas these states represent this portion, or the states represented by the white portion, they are known as the hole-like states. Electron-like states means if conduction is to take place, then conduction will take place with the help through electrons here. And in this region, the conduction will take place through holes. And we will understand the concept of hole in maybe in the tomorrow's lecture. Now the question arises, how do we go from the Fermi surfaces for free electrons? And remember, the Fermi surface for electron is a circle in 2 dimension and a sphere in 3 dimension. Now we ask question, how do we go from Fermi surfaces for free electrons to Fermi surfaces for nearly free electrons model, or the Fermi surfaces in the presence of weak periodic potential? So we can make approximate constructions by the use of the 4 facts. We need to remember these 4 points. The interaction of the electron with the periodic potential of the crystal creates energy gaps at the zone boundary. This we have already seen. Almost always the Fermi surface will intersect the zone boundary perpendicularly. So that we can explain. So for example, not in this picture, let me find. So for example, if this Fermi surface is extending, then it will extend this zone boundary perpendicularly. It will not go like this. It will not go in the oblique direction, but it will intersect the zone boundary perpendicularly. The crystal potential will round up sharp corners in the Fermi surfaces that we have seen in the previous slide, where in the absence of periodic potential, the corners were very sharp, but the presence of periodic potential will make these corners in the round shape. The total volume enclosed by the Fermi surface depends only on the concentration of the electrons and is independent of the interaction of electrons with the lattice. Now, what we are doing is we are seeing basically the consequences of the nearly free electron model. That is, earlier we discussed the free electron model, and now we are considering the presence of weak potential when we turn on the weak potential. So first we consider the case of monovalent metals. We can see monovalent metals means they contribute in these metals, each atom contribute 1 electron to the solid. So for example, sodium has atomic number 11 and it has 1 electron in the 3s shell, so it will contribute 1 electron. Away from the Brillouin zone boundaries, the electronic bands or the dispersion relationship are very similar to those of free electrons that we have already seen. Band gaps open up at the Brillouin zone boundary. Each band in the Brillouin zone will contain 2n electron states, because in the first Brillouin zone there will be capital N number of K values. In the EK diagram, in the first Brillouin zone, we will have K values equal to capital N, where capital N is the number of primitive unit cells in the crystal. Or in other way, we are having a crystal that contains N number of primitive cells. So if we want to see how many number of K points lie in the first Brillouin zone, that would be equal to the number of primitive cells in the crystal. And since each K point can hold or can occupy 2 electrons as per the Pauli exclusion principle, therefore the electron concentration in the first Brillouin zone will be equal to twice of capital N. And These alkali metals or the monovalent metals, they show the BCC lattice, body-centered cubic lattice. They are, for example, sodium, potassium, they are not known as alkali metals. They are monovalent uh, metals. They have one electrons per primitive cell. As a result, their Fermi surface encompassing n states have a volume which is half that of the first Brillouin zone. What we are saying, each Brillouin, the first Brillouin zone can hold 2n electrons, and since the in case of monovalent atoms or monovalent metals, we will have only n number of electrons. So only half of the k states would be occupied. Therefore, the volume of the Fermi surface would be half that of the first Brillouin zone. And what is the what is the lattice of what is the reciprocal lattice of a BCC lattice? It is the rhombic dodecahedron for a BCC lattice in reciprocal lattice space, or it is the Wigner seed cell of a BCC lattice. The convenient unit cell of a body-centered cubic lattice is a cube of side A containing two alkali metal, one at the one atom at the corner and the other atom sitting at the center of the sitting at the body center. So the body-centered cubic lattice is a cube of side A containing two alkali metal atoms. The electron density is therefore, because each unit cell is contributing 2 electrons, so 2 divided by the volume of the unit cell, that would be the electron concentration. And if we substitute this n in the expression for the Fermi radius, Kf is equal to, if you recall our discussion on Sommerfeld free electron theory, Kf was 3 pi square capital N divided by V to the power 1 by 3. So here we can write 3 pi square N over A cube to the power 1 by 3. We find that Kf is equal to 3 pi square, and in place of N, sorry, it should not be here. A cube should not be here, otherwise it is mistake. See, it is 3 pi square N to the power 1 by 3. So in place of N, we write 2 over A cube. So this would be 2 pi square dot 2 A cube. And after solving it, we will get 1.24 pi over A. Now we need to find the shortest distance from the origin to the zone boundary in this rhombic dodecahedron BCC lattice, and that would come out to be d is equal to 2 pi over a 1 under root half square plus half square plus 0 square, that would be 1.41 pi over a. So this d represents the distance from the origin to the zone boundary, and this is the radius uh, of the Fermi sphere or Fermi circle. And you can see that Kf is smaller than d. That's why the Fermi sphere or Fermi circle will lie inside the first Brillouin zone. So we have seen that value of Kf is smaller than d. And this implies the following facts. Number one, the Fermi surface is entirely contained within the first Brillouin zone. Second, it covers 88%. If we divide 1.24 by 1.41, we will get 0.88. So the Fermi circle, it covers 88% of the shortest distance from the center of the zone. And it is separated by a distance equal to 0.174 pi over a from the zone boundary. The populated electron states therefore lie well clear of any of the Brillouin zone boundary, thus avoiding the distortions of the band due to the band gaps. Hence, the alkali metals, especially sodium, have properties which are quite close to the predictions of Sommerfeld model, that is, Fermi surface are spherical in shape. Therefore, in case of alkali metals, especially sodium and potassium, we see that their Fermi surface is almost spherical in shape. It varies only 3% from the spherical shape. And this is what has been shown here. For potassium, it is almost spherical. The Fermi surface completely lies in the Wigner seed cell of BCC lattice, that is a rhombic dodecahedron. But lithium is also the example of this alkali metal. But in case of lithium, there is a slight distortion because there is a strong periodic potential present in case of lithium. So the Fermi sphere is slightly distorted. So it is exactly spherical for uh, potassium metal in the nearly free electron model, and the periodic potential for lithium metal is slightly stronger than potassium, and correspondingly the Fermi surface is distorted towards the zone boundary. Now we see what is going to happen when we have a Fermi sphere that is whose surface is lying close to the zone boundary. Whenever a periodic potential is added, we know gaps open up at the zone boundaries. This means that the states which are close to the zone boundary get moved down in energy, and the states and the closer they are to the boundary, the more they get moved down. For this, again, I need to uh, show you this graph. So whenever we are very close to the boundary, the states which are close to the boundary, they are moved down in the energy. And in the second Brillouin zone, which the states which are very close to the first Brillouin zone boundary, they are moved up in energy. So this is what I am saying here. This means that states close to the zone boundary get moved in energy, and the closer they are to the boundary, the more they get moved down. As a result, the states close to the boundary get filled up preferentially at the expense of states further from the boundary. All this statement can be understood with the help of these three diagrams. So for example, this is the free electron Fermi surface that is lying inside the first Brillouin zone. When we turn on the periodic potential, so these states are very close to the zone boundary in comparison to the states which are very far from the zone boundary. So these states would get distorted, means these states would be occupied more in comparison to those states. So the electrons will move from these states to these states because these are the states with low energy. So preferentially these states would be filled first in comparison to those states which are very close to the zone boundary. We increase the potential more than the remaining states. These states again would shift here because this portion is the nearest one to the zone boundary, and these states would be filled and these states would become empty, these states. So this is the variation of Fermi surface. Here the potential is zero, here the potential is weak, and here we have the strongest potential where the Fermi surface will interact with the zone boundary, and it will interact with the zone boundary. The zone boundary is like this, and the Fermi surface is moving perpendicular in the perpendicular direction. So it will bisect the Fermi surface in the perpendicular direction. Whenever a Fermi surface touches the Brillouin zone boundary, it must do so perpendicularly. That statement we have already understood. This is due to the fact that group velocity is zero at the zone boundary. Uh, the energy is quadratic as one approaches normal to the zone boundary. Since the energy is essentially not changing in the direction perpendicular to the zone boundary, the Fermi surface must intersect the zone boundary normally. Similarly, we can understand the case for monovalent metals but having abscissa lattice. Abscissa lattice means face centered cubic lattice, and noble metals are the examples of uh, monovalent metals which are having the abscissa lattice. For example, copper, or you have silver, or you have gold. They possess abscissa structure. The first Brillouin zone of this abscissa lattice is a truncated octahedron which has 14 faces including 8 hexagonals and 6 squares. There are 4 atoms per unit cell in a abscissa structure. We know that. Therefore, the radius of the Fermi sphere would be 3 pi square dot 4 upon a cube to the whole cube 1 by 3, and if we calculate it, it would come out to be 1.563 pi over a. Now, because we are having different faces, there are 8 hexagonal faces and 6 square faces. So we need to find their distance, means we need to find the distance from the origin to a hexagonal face, and we need to find the distance from the origin to the square face. So the uh, for the square face, d would come out to be 2 pi over a. 2 pi over a. This means that, and similarly, the shortest distance of a hexagonal face would come out to be 1.732 into pi over a. So the square faces are further from the origin in comparison to the hexagonal face, because for the square face the distance is 2 pi over a, but for the hexagonal face it is 1.732 pi over a. Again, we can see that for any face, be it square face or hexagonal face, the radius of the Fermi sphere is smaller than the distance, smaller than d. But you can see what is the distance from the origin to the zone boundary. It is pi over a, and the radius of this sphere is 1.563 pi over a. Therefore, the Fermi sphere or Fermi circle will lie in the second Brillouin zone, and this implies that Fermi surface is not, it will not lie in the second Brillouin zone, it will lie in the first Brillouin zone, because the total distance of the Brillouin zone is 2 pi over a. So the Fermi sphere for the abscissa lattice, it will lie inside the first Brillouin zone, but its radius is larger than that of BCC lattice. The Fermi surface is entirely contained within the first Brillouin zone. It covers 90%, 1.24 divided by not 1.41, it should be 1.732. It should be 1.732. This is by mistake. I copied it from the BCC, and that's why it is like this 1.41. It should be 1.563 divided by 1.732. So it covers 90%. Please correct it. It is 1.732. 563 divided by 1.732 of the distance from the hexagonal face from the center of the zone, and it is separated by distance of 0.1693 pi over a from the zone boundary. Therefore, in the BCC metals, the Fermi surface is slightly more closer to the zone boundary than in alkali metals, because here the radius is larger. It is 1.563 pi over a, whereas it was 1.2524 pi over a in case of BCC metals. It is separated by a distance of 0.169 pi over a from the zone boundary. Therefore, in the FCC metals, the Fermi surface is slightly more closer to the zone boundary than in alkali metals. Additionally, the effective potential is greater in the case of FCC lattice due to more complex shape of ionic structure. Copper, then silver, then gold, they have electrons in 3D, 4D, and 5D cells where the shape is different. Therefore, the effective potential in case of these noble metals is greater due to more complex shape of ionic structure. These together, one thing, that the Fermi surface is closer to the zone boundary, and the other thing, effective potential is greater. These two things together suggest that Fermi surface near the centers of the hexagonal face must be substantially distorted. And experimentally, it is shown, experimental results also verify these theoretical assumptions. And experimental results show that the Fermi surface near the hexagonal face opens up. It is distorted. So this is a hexagonal face. This is also hexagonal face. You see, the Fermi surface opens up. The Fermi surface opens up and stick to the zone boundaries, like in this case. Fermi surface opens up. So this is for one Wigner sheet cell or one unit cell of the reciprocal space. When we form the complete lattice, then we will see. So this is, again, this is the colorful picture, and it would be more helpful to understand. You see a hexagonal face. Here the Fermi surface is more closer, so it intersects the zone boundary. That's why it opens up here. It opens up here. But since this Fermi surface is far from the square Brillouin zone boundary, therefore it is distorted, but it is not touching the Brillouin zone boundary. So Fermi surface opens up only in the hexagonal faces. And this is the Fermi surface of, this was the Fermi surface of copper. And it is shown here in the periodic zone scheme, where you repeat the unit cell, and the two Fermi surfaces, they will interact, and this portion is known as neck. This portion is known as neck, and the remaining portion, which is kind of spherical in shape, that is known as a belly shape. So Fermi surface, sometimes you will see that for copper, only this portion will be shown. It is kind of a bone. It is kind of a bone. So this is the Fermi surface of copper metal. And the portion, these portions which connect different primitive cells in the reciprocal space, they are known as necks, and these portions are known as belly. The diameter of this neck strongly depends upon the lattice potential. Experimentally, it was observed that in case of copper, silver, and gold, that neck diameter increases because of increasing in the atomic number and lattice potential. The square faces are more distant, and the Fermi surface does not neck out does not neck out to meet the Brillouin zone boundary as is shown here. You you have class after 11:30? Do you have a class after 11:30?
Yes, sir.
Okay, but I think I should continue. I would like to finish it. So we have seen the examples of the distortion, how the distortion would occur in case of monovalent metals. Now we can consider the case of a case of divalent atoms and then polyvalent atoms. In case of divalent atoms, the number of electrons is precisely enough. So in case of, for example, sodium, it was only half area or volume of the Fermi sphere or Fermi circle was of the first Brillouin zone was occupied because each atom was contributing one electron. But in case of divalent atom, each atom is contributing two electrons. Therefore, the first Brillouin zone would be completely filled. The number of electrons is precisely enough to fill a single zone. In the absence of a periodic potential, the Fermi surface is still circular or spherical, although it now crosses into the second Brillouin zone. When a periodic potential is a gap opens up at the zone boundary. This gap opening pushes down the energy of states within the first Brillouin zone, and the energy states are pushes up which are in the second Brillouin zone but close to the first Brillouin zone boundary. That, please recall that previous picture. If the periodic potential is sufficiently strong, then the states in the first Brillouin zone are all lower in energy than states in the second zone. As a result, the entire first band is filled and the upper band is empty. Since there is a gap at the zone boundary, there are no energy excitations possible and the system is an insulator. This is what I am saying. The Fermi circle or Fermi surface, Fermi sphere for a divalent metal, it would protrude in second Brillouin zone also. And when we apply a strong potential, all these states will go higher in energy, and the states which are lying in the first Brillouin zone, they will go down in the energy. Therefore, all these states would be occupied. And since the first Brillouin zone is completely occupied by the electrons, and then we have a gap, therefore, this is kind of a insulator. And again, this is how the Fermi sphere is going to distort. Fermi surface is going to distort. All right. So this is for very strong periodic potential. Now we would like to see if the potential is not very strong, potential is between the intermediate range, what is going to happen? So we ask a question, what happens for the intermediate strength of periodic potential? States outside of first Brillouin zone are raised in energy, and the states inside the first Brillouin zone are lowered in energy. Therefore, fewer states will be occupied in the second zone and more states will be occupied in the first Brillouin zone. So this is under a medium range periodic potential, the Fermi surface structure of a divalent metal. You can see that these states will not be occupied. The corners will not be occupied. It is very interesting thing. Please understand it. When we have the strong potential, the first Brillouin zone was completely occupied. But when we have the intermediate strength of periodic potential, then these states will remain unoccupied, shown by the white color, and some of the states in the second Brillouin zone will be occupied. So these are the hole-like states in such metals under intermediate periodic potentials. What we can have? We can have the electronic transport due to the holes. That's why some of these metals will exhibit positive value of hole coefficient. And recall, it was the one of the shortcoming of Sommerfeld quantum free electron theory, which predict the negative value of hole coefficient for all metals. But here we see that when we have the intermediate strength of the periodic potential, then in such metals, the transport of current would be by hole-like particles, and they will exhibit the positive value of hole coefficient. That's why in case of magnesium, beryllium, we observe positive value of hole coefficient. So this is in a PDO extended zone scheme. It can be converted into, for second zone, only for second zone, it can be converted into the reduced zone scheme. This portion will come here, this portion will go here, this portion will go here, this portion will go here in a reduced zone scheme. And since the states here are empty at the corners, they exhibit metal-like behavior. But if the for certain solids, for certain divalent solids, if the periodic potential is very strong, they will not behave like metals, but they will behave like insulators. This is the Fermi surface for polyvalent metals, and you can see it gets very much complicated for polyvalent metals. It is not spherical, but you see how complicated shape it has. I have a couple of slides, I think 3 or 4 slides more. So now we can see if we apply electric field on a Fermi surface, what is going to happen. So this is in the presence, in the absence of electric field for any type of metal. Here all the states are empty, therefore electrons can go from this state to empty states, so conduction is possible. But when we apply electric field in this direction, so you see how the Fermi surface would get distorted, because electron would move, the average K vector would move in the opposite direction of the electric field. Therefore, the Fermi surface will get distorted. And because these states are possible here, these states are empty here, the electrons can go from the sky blue region to these states. Therefore, conduction is possible, and Fermi surface will get distorted, but it will lead to a metallic or conducting behavior. Simultaneously, we can see what is the effect of magnetic field on the Fermi surface, how the Fermi surface is going to get modified. So, for example, if tomorrow we will understand this equation, the equation of motion of electron under the application of electric field is given by h cross dk by dt, that is the rate of change of k wave vector occupied by the electron is given by Lorentz force minus ev cross b. So if electron is moving from the filled state to the empty state in this direction, and the magnetic field is applied, that points in the direction in the plane of this laptop. So in the plane of the inward direction of the plane. So then V cross B would be in this direction. V cross B would be in this direction. This means that electron would move on the surface of constant energy. Electron would move on a surface of constant energy. So the change in K is perpendicular to the direction of V and B. The electron stays on the constant energy surface. Here also you can see if the some Fermi surface is of this shape, then the V is in this direction. V cross B would be in this direction. The electron would move on a surface of constant energy. And you see, if the electron is moving, if the particle, I am saying particle, if the particle is moving here and if the particle is moving here, what is the difference? This will form an electron orbit whenever the particle is moving deep inside the Brillouin zone. So the particle is moving on a constant surface like this, and all the states are occupied here. The occupied states are represented by the sky blue circle. So the electron is moving in this direction. But here I told you these empty states are the hole-like states. So if the electron is moving here in the hole-like states and all the regions are outside region are occupied by the electron. So if electron is like moving here, it will move in the opposite direction. Here you see the electron is moving at the boundary of a filled state. It is moving in this direction, and here it is moving at the boundary of an empty state. It is moving in the opposite direction. So whenever the electron is moving in such a way, it behaves like it is moving, it is having a positive charge. So this positive charge is a hole. That's why I said you, if we are getting a Fermi shape like this for certain metals in which the corners are empty, then they will exhibit the positive value of hole coefficient, because in those metals, electron would behave as if it is having positive charge or it is equivalent to a hole. Two more slides. What about the electrons in the second zone in a metallic system? So this you can see the electrons are moving like this. The electrons are moving like this in the second zone. And if we represent it in the periodic zone scheme, so this is, they are moving on a surface of constant energy in the periodic zone scheme. This portion can be translated here, and this portion can be translated here. So you can see that the electron is moving on a surface of constant energy in second Brillouin zone also. This is electron-like behavior, and here it is the hole-like behavior, and hence the strange hole coefficient for certain polyvalent metals. So the last slide is also very important. If the electron or hole is moving like this, and whenever it comes close to the zone boundary, it will be Bragg reflected. It will be Bragg reflected. So when the electron comes here, so it would be reflected back here. Now it will start moving in this direction. So whenever any electron traveling in a Brillouin zone, it reaches at the zone boundary, it suffers the Bragg reflection. Therefore, it is Bragg reflected. And Bragg reflected can be represented here, that this point is equivalent to this. So again, it will start moving here. When it moves here, again, it will be reflected here. So it will come here, it will come here like this. And because all these lines are equivalent, and electron will move like this. It will be reflected, it will go here, then it will go here, it will be reflected, it will move in this direction, and then it will be reflected. So it will move in this direction. So this is all about the Fermi surface and their construction using the Harrison construction and all other things. We have discussed so many things, and most of the part you can get from the Kettle's book. It requires your attention. This lecture is a little bit complicated. That's why it requires your thorough attention if you want to understand how we construct the Fermi surface.